All right, so our goal is to find the domain and range for each of these functions. And remember, you want to be um, thinking about, like we did in our notes, what type of function it is, and then therefore, starting with domain, what the restrictions are. All right, so f of x equals x minus 1, that's linear. That's linear, so the domain is all real numbers and the range is all real numbers. This line looks something like this. It's got a positive 1 slope, so no issues there. When we make it 1 over x plus 1, this is now rational. So remember, or x minus 1 rather, x minus 1 cannot equal 0 because we don't want to divide by 0. So x can't equal 1. In interval notation, that's negative infinity to 1 and 1 to infinity. And then when we think about range, this is a little bit, range can be harder for people. I always start with the numerator. If there's no variable in the numerator, then there's no way that this fraction can divide out to be 0. So y will not be 0. I can get something very close to 0. 1 divided by 100 billion is very close to 0, but it's not exactly 0. Okay, now what about how it divides out? Can we get y values that are positive or negative? We can get both because the top is always positive, positive 1, and we're dividing it by either positive or negative depending on what you put in for x. If you're still not sure about that, pick numbers that are in the domain and start calculating some things. If I pick 0, I get negative 1. If I pick 2, I get 1. If I pick negative 2, I get negative 1/3. If I pick positive 2, I get, oh, I already did that. If I pick positive 3, I get 1/2. So you can kind of go through until you've convinced yourself that you'll get both positives and negatives. So y can be anything, large or small, but just not 0. And if you pick a really tiny value so that x minus 1 comes out small, like if I pick something close to 1, like 1.1, for example, 1 divided by 1.1 minus 1, that's going to come out to 10. And if I keep going, if I pick 1.000001, that's going to give me 1 divided by a tiny decimal. A number divided by a tiny number, like a decimal or a fraction, is equal to a big number. A negative number divided by a tiny number, or a positive number divided by a tiny negative number, is going to be a really negative value. Okay, that was a long explanation of basically saying y can be anything but 0. If you're ever not sure on these, go ahead and graph these in your graphing calculator and just examine the graph. Take a look at what we're looking at and kind of confirm, because you'll start to see some patterns. What if we switch this to the square root of x minus 1? Remember, we look at the expression underneath the square root for domain, set it greater than or equal to 0, and solve. So the domain is 1 to infinity. What does that mean for the y values? Well, for square root functions, you can kind of start by plugging in the first number in the domain. If you plug in 1, you do get the square root of 0, so y can equal 0. This is a positive square root, so any number you pick after 1, 2, 3, 4, 5, 1.1, whatever, you're going to get y equals the positive square root of something. So that's a number that's greater than 0. So our range, the lowest it can get is 0, and then it only goes positive after that. Again, graph that if you're not sure, and just see that it's a graph that kind of looks like this. And then what if we have a combination like we did in our notes? This is rational and a square root, so we have to make sure that x minus 1 stays positive, but it can't equal 0 this time because then we would be dividing by 0. So x is just greater than 1. And then for the y values, I'm going to kind of treat this like I did for part B. So B and C, or B and D, are pretty similar. Y can't equal 0 because there's no x in the top of the fraction so that I can plug in a number for x and get 0. It's always going to be 1 divided by something. So y can't be 0. And then what did we say about this square root in part C? We said, oh, the y values are always going to be positive because it's the positive square root of something. So you always have a positive divided by a positive. That's always going to come out positive. So the range values are going to be anything above 0 and never any negatives. For E, we have an odd root. Odd roots have no restrictions. We can odd root a positive or a negative or 0. So the domain is all real numbers. And the range is going to be all real numbers for the same reason. We can take an odd root and get negatives. We can get positives. We can also get 0. What if we put the odd root in the denominator? Okay, so remember, for domain, we can't divide by 0, but there's no odd root restriction here. So I can put positives or negatives in for x. I just have to make sure that x minus 1, the number underneath the expression underneath the odd root, that doesn't equal 0, because I don't want to get 1 divided by 0. So the only restriction is that x can't equal 1. So that's negative infinity to 1, 1 to infinity. What about the range? There's no x on top, so there's no way we can get y equals 0. So y can't equal 0 because it'll always be 1 divided by something. Cube roots can produce both positives or negatives. So we always have this positive 1 divided by sometimes a positive value or sometimes a negative value. That means we're going to get both positives and negatives. So the range is negative infinity to 0, 0 to infinity. I just want to stop and graph this last one. Again, you can graph any of these. If you're trying to graph, make sure plot 1 is turned off. You can just unhighlight that. And then we were trying to do 1 divided by, now cube root is in the math menu. Or remember, you can also just say a cube root is the same as raising something to the 1/3 power. So whatever, however you want to do it. And then because my window's probably weird from the scatter plot we did, I want to zoom 6, which is standard. Just go back to a 10 by 10 grid. This is what that last graph looks like. And the graph doesn't stop here. It just is getting too small for the pixelation to be able to carry on. But anyway, take a look at what's happening. We get values that are close to 0 but negative, and then they head to negative infinity. We get values that are up at infinity, and then they get very close to 0 but stay positive. So that's what we're saying when we say something like this. And you can see the closer the numbers are to 1, the more they shoot to infinity or negative infinity. If I pick 1.00000001, I'll be way up here on the graph. If I pick 0.9999999, I'll be way down here on the graph. And then the bigger number you pick, it'll be 1 divided by a big number, so you'll be close to 0. Okay, let's start a new set. So notice with these, it's like we have the same expression throughout. We're just putting it under different things. Okay, so 3x plus 2 is linear. All reals for domain and range. Easy, easy, easy. When we take that linear expression and put it in a denominator, we set the denominator not equal to 0 for our domain, and we start solving. Subtract 12, divide by 3. So x could be anything but negative 4. Let's write that down for domain. And then for range, I go back through my checklist. There's no x on top, so y can't equal 0. 3x plus 12 can be positive or negative, so you're always going to get 1 divided by a positive, or sometimes it'll be negative, and that comes out to either a positive value or a negative value when you divide it out. So negative infinity to 0, 0 to infinity. What if we put 3x plus 12 under a square root? We know that for a square root function, 3x plus 12 has to remain greater than or equal to 0, which means x has to remain greater than or equal to negative 4. In interval notation, that's a square bracket on negative 4 to infinity. And then for the range, just like for part C in the previous one, you have the square root of just something linear, a little linear expression. So that's always going to give you a y value that's at least 0. It's a positive square root, right? There's no plus or minus. There's no negative sitting in front. So you can only get positive values out. So 0 to infinity. All right, what about the next one? Now it's not just the square root, but 1 over the square root. The only thing that changes for the domain is that 3x plus 12, it can't be greater than or equal to 0. It's just got to stay greater than 0. It's got to be greater than 0 so we can square root it, but it can't equal 0 because we don't want to divide by 0. So parentheses, negative 4 to infinity. Okay, and then what about our range? Kind of the same idea to start off with as part B. There's just a 1 up here. There's no x. So there's no way you can get y to divide out to exactly 0. It'll only ever get close. And then you've got 1 divided by a square root. That square root is always positive again. So that's always going to be something bigger than 0. So the range for this is not including 0, 0 to infinity. For part E, we have an odd root. Odd roots have no restrictions, and their graphs go on forever. I'll just show you this one too. So this was 3x plus 12. Now there's no, there might be a way to do a fifth root. I think there is an nth root. Yeah, right here you could, but I think it's just easier just to say to the 1/5 power. This graph will gradually decrease and gradually increase. So its range is all real numbers. There's no horizontal asymptote there. All right, and then 1 over the 5th root. So again, 3x plus 12. It can be positive or negative, but it cannot equal 0 because it's in a denominator under an odd root. So x can't equal negative 4. And then for the range, again, no x up there means y can't equal 0. Now it's going to be 1 over a 5th root can be positive or negative depending on what you're putting in for x. If I put in negative 10 for x, I'm going to get the 5th root of something negative. So 1 divided by a positive or a negative, it will come out positive or negative depending on what that is. So we've got negative infinity to 0 and 0 to infinity. All right, now we're looking at x squared minus 9. So this is the first one where the first function is not linear. This is quadratic, right? For quadratics, it's a good idea to remind yourself maybe of what the graph looks like. X squared minus 9 is a parabola that opens up, but its vertex is down there at 0, negative 9. Okay, so why is that important? It's not important for domain. Domain, all real numbers. It is important for the range, though. The range is not all real numbers because parabolas have a low point or a minimum or sometimes a high point if they're opening down. So this graph, the lowest y value on the graph is negative 9, and then we go up to infinity. All right, if we put that in a denominator, now x squared minus 9 can't equal 0. I think we had this one on our notes. So now x can't equal plus or minus 3. And remember in our notes how we had to write that. You should have, if you have two excluded values, you should have 3 parts to your domain. Negative infinity to negative 3, negative 3 to 3, and 3 to infinity. These are all the numbers. It's this middle part that some people forget. These are all the numbers but negative 3 and 3. And then we're not going to do the range for this one. If you see something blacked out, not that we can't puzzle our way through the range. If you want to try it, you can and check on the graphing calculator. But just know that I'm not really going to be asking you range questions like that. Or if I did, it might be for bonus or something. What about 9 minus x squared? So 9 minus x squared has to say greater than or equal to 0. Now this is kind of tricky. I didn't show you guys how to do quadratic inequalities. We will get to that later. You might remember from last year that you still figure out like, okay, x equals plus or minus 3 are the zeros. And see if this looks familiar to you. You stick those on a number line, and then you like test intervals, or maybe you sketch a little negative x squared graph, and it comes out minus, plus, minus. And then you want the section in between. Okay, if that's not familiar, like I said, I will teach you that formally a little bit down the road. But here's a graph that I want you to have memorized. We're going to see this a lot. And actually, we see it in this specific expression is in a calculus problem that my students always forget about and miss. So I've decided to start teaching this and kind of hammering this in pre-calc. Okay, so what if you don't go the way that you might have learned last year? This graph, when it's the square root of a perfect square minus x squared, it looks like a half circle. The radius of the half circle is what you would get to be 0, so plus or minus 3. The maximum height when x equals 0, you get square root of 9, 3, and it's this cute little half circle. So if you can, that's something I want you to study. If it's a difference of squares and the number is first, and it's under a square root, that's a half circle, right? We know that a circle equation is like x squared plus y squared equals 9. That's the full circle, and all we did here was solve for y and square root, and that gives you the top half of the circle. If you're looking at that graph, it's super easy to do domain and range. The domain goes from -3 to 3, and the range, the lowest y value is 0, and the highest y value is 3. Okay, now I'm not going to think about the graph for these last 3 in this one. So for this one, I'm going back to saying, okay, x squared minus 9 has to stay just greater than 0 because I can't divide by 0. But I'm using what I know from part C. X squared, or I'm sorry, I'm not using exactly the graph from part C because it's flipped around. So what about this? Let's see. X squared minus 9 greater than 0. So we know that x equals 0 at -3 and 3. Okay, but what about in between? If you plug in 0 for this and for x, do you get a real number? No. So that's out of the domain. If you plug in something bigger than 3, do you get the square root of something positive? If you plug in 4, you get 16 minus 9. That's the square root of something positive. So we can plug in anything bigger than 3. And if we plug in anything smaller than -3, like -4 or whatever, the same thing's going to happen. We'll get positive 16 minus 9. So this domain is anything from -infinity to -3. Oh, not including though, sorry, because we're just talking greater than 0. And then anything from 3 to infinity. But not the in-between part, because if you plug in numbers between -3 and 3, you'll get 1 divided by the square root of a negative. We're not doing range for that because, again, it's a bit complicated. So think of that on your own if you want something extra to think about. What about the cube root of x squared minus 9? We can cube root, we can odd root anything. And we can plug anything into x squared minus 9 on its own. So this is all real numbers. And then what about 1 over the cube root of x squared minus 9? So if it's an odd root, I don't need x squared minus 9 to be positive. I just have to make sure x squared minus 9 is not equal to 0. So that means x cannot equal plus or minus 3, but it can be anything else. So this is going to look like b. So we can go -infinity to -3, anything between -3 and 3, and anything from 3 to infinity. Okay, I wouldn't give you a range question for that. All right, what about 4a? X squared minus 8x plus 15. Domain is easy, all real numbers. What about range, though? Now, again, some of these questions I'm kind of giving you are because I know you did this stuff last year, so it might be familiar, but I'm also going to formally teach it to you when we do quadratics later. So we're sort of getting ahead of ourselves a little bit, but I think we can handle that for our AP pre-calc anyway. Okay, I know this is a parabola that opens up, right? Therefore, I know that whatever this y value is for the vertex, I know that the graph is going to be something to infinity. So how do I figure out the y value for a vertex? There is a vertex formula, or you could use complete the square, but there's a vertex formula. The vertex formula This is something else to kind of study. We'll get into it in a few weeks, but the x-coordinate for the vertex is always going to be negative b divided by 2a, where b is the number in front of x and a is the number in front of x squared. And then once you figure out that x-coordinate, because that's an x-coordinate, right? Once you figure that out, you plug that in, f of negative b over 2a. You plug that in to figure out what the y-coordinate is. And it's the y-coordinate that we actually care about. So let's take a look at our problem. Our vertex is the opposite of negative 8. So negative 8 is positive 8. Over 2 times, there's just a 1 in front of the x squared. So 8 over 2. So our vertex has an x value of 4. And then we plug in f of 4 to figure out what the y value is. So if I plug 4 into this, I get 16 minus 32 plus 15. 16 minus 32 is negative 16, plus 15 is negative 1. So the range is negative 1 up to infinity. I know that parabola opens up because it was a positive x squared. Okay, so I'm going to put a star next to this one because anytime you have a trinomial like that, x squared plus or minus something x plus a number, you're going to have to do the vertex formula. All right, number 4 carries on to the next page, so I'm going to try to keep this on my same page. Sorry, you might have to flip back and forth, but keeping in mind, we're not doing range for this one, we're just doing domain. And so on this, we're saying, well, we can't have x squared minus 8x plus 15. We can't let that equal 0. So to figure out what makes it equal to 0, we need to factor it. It should be x minus 5, x minus 3 can't equal 0, and therefore x can't equal 5 or 3. When you're writing this in interval notation, make sure you go in order. We always start with negative infinity. The first number I would hit is 3, and then we can have anything between 3 and the next number, which is 5. And then we can have anything from 5 to infinity. What about the square root of that quadratic? Well, we need this quadratic piece to stay greater than or equal to 0. So again, we know that the zeros are 3 and 5. Those are the two numbers I plug in and I get 0, so those are in the domain. How do the numbers that are in each section work out? So, like, what if I plug in 4? Do I get a positive or a negative if I plug in 4? Well, if we plug in 4, we already did that, didn't we? If we plug in 4, we get negative 1. That means that anything between 5 and 3 is going to be negative. So that whole section is out. We can't plug in anything between 3 and 5. What if we plug in something smaller than 3? Like, what if we plug in 0? Then you get the square root of 15. So yeah, anything smaller than 3 is going to give you something positive. Anything bigger than 5 is also going to give you something positive. How do I know that? I can test a number. I can plug in 6. 36 minus, oh wait, what did I say? I can plug in 6. Yeah, so 36 minus 48. What is that? That's negative 12, but then plus 15 gives you a positive. You probably also learned like, oh, it's an x squared graph. I can sketch like a graph like this. That's okay too. You can see that that graph is positive on the left and positive on the right. Okay, so negative infinity to 3 and 5 to infinity. Ooh, what about the range for this one? I didn't black this range out because, again, this is something that's going to be kind of cool. I want to show you this graph. Let's graph this thing. The square root of x squared minus 8x plus 15. Let's just graph. Zoom 6. Anytime you have the graph of a quadratic where it's a positive x squared, so it's no longer a semicircle. If it was a perfect square minus x squared, it'd be like a little half circle. But this is like, gosh, it almost looks like a piece of a hyperbola, right? I think it is the top half of a hyperbola. Anyway, this graph will always look like this. And notice that it should be connecting. Again, it doesn't always look like that. because of the pixelation, but it's connecting at 3, and then it picks up again at 5. So what are the x values on this graph? Anything to the left of 3 and anything to the right of 5. You can also use the information from the previous part C to help you, or I'm sorry, from your domain to help you figure that out. If you plug in anything between 3 and 5, you're getting the square root of a negative, right? So that's not going to be in our range. Where do these two chunks start? Well, they start at 0 and they both go up, right? Because we can get 0 for this quadratic. We can't let it be anything negative, and a square root is always positive. So 0 to infinity. For all of the square root problems that I give you, if it's the square root of something, I'm going to give you an expression that starts at 0 and goes up. The only time it can go down or start somewhere other than 0 is if I give you something more complicated, which I won't for what we're doing here. What if we have an odd root? Then all bets are off. We can odd root positives and negatives, so all real numbers. Okay, now that quadratic is hard, I think, because it had 3 terms. Sometimes this quadratic was positive, sometimes it was negative. This quadratic is going to be really easy, and we're going to have something like this probably on our homework quiz. So I want to pay attention to this, and we're going to see this a few times. X squared plus 4, think about that graph. It's a parabola that's been shifted up 4. It is always positive, right? You can plug in anything for x. You can plug in negative 1 trillion, and when you square it, you're going to force that to be positive, and then you add 4, and it'll still be positive. So that doesn't affect my domain. My domain's all real numbers because it's quadratic. But for the range, that's easy to come up with, like, well, it's always positive, and I can just see, I don't need a vertex formula. I can just see that the vertex starts at 4 and goes up from there. But the fact that it's always positive is nice to know for the rest of these. So what if I do 1 over x squared plus 4? Normally we would say x squared plus 4 can't equal 0. But it never equals 0. It's always positive. Or if you start trying to solve for this, you're like, well, I'm going to get an imaginary number, right? We'll talk more about imaginaries when we get to quadratics, but if you get an imaginary number, that just means it's still all real numbers. There's nothing I need to exclude from my domain to keep the answer as a real number. The answer is always real. What about the range for this one? This is kind of tricky though, right? I said it's always positive. What's the lowest y value we can get on the graph? 4. On the x squared plus 4, excuse me. So we can get 1 over, if we put in 0, we can get 1 over 4. If we plug in something bigger than that, right? If we plug in 5, we get 1 over, let's see, if we plug in 5, we get 1 over 29. That's a smaller fraction, right? So what is our range going to look like? You want to graph this one to see? Because again, when we do this for the first time, it can be kind of weird. Let's see what it looks like. That's weird, right? It looks like a straight line. What if I change my window? We don't need to go from negative 10 to 10. What if we go from like negative 1 to 1? That's better. Here's 1/4. And then when I plugged in, what did I say I was going to plug in? When I plug in 5, I think. If I plug in 5, I was something close to 0. If I just plug in like 1, I get 1/5. So 1/4 is the biggest that this thing will ever get. And then the further out you go on x, the smaller that fraction is going to be. It's going to get closer and closer to 0. So interesting. So this range is 0, but it'll never hit 0. And then you're only ever going up to 1/4. So that's a little different. If I go through my stuff again, hold on, let me go through my checklist again. Y can't equal 0 because there's a 1 over something. And I always have this positive right here. So 1 over a positive, normally I would say 0 to infinity, but this one sort of has a cap on it. Okay, so it should be 0 to 1/4. What about the square root of x squared plus 4? This is the square root of, normally we would say x squared plus 4 needs to stay greater than or equal to 0, but remember, x squared plus 4 is always positive. So we can plug in anything for that square root, and we'll get a real number out. Now again, we want to think about, well, what are the values that we can get for this? Can we get y equals 0 out of this? No, because remember, we can't plug in anything for x to make this negative 4 plus 4. So we're not going to get 0 on this one. Will we ever get any negative values? No, because y is always going to be positive. Square root of a real number will always be positive. Then is there any minimum value on this one? If we plug in 0, we get square root of 4. If we plug in like 0.1, we get square root of 4 point something, which is like 2 point something. Can we ever get smaller than 0, 2? I don't think so, because you can't ever get a negative out of x squared. So this one goes from 2 up to infinity. If I plug in 100 for x, I'll get a large number, square root of something large. Okay, what about the cube root? Well, normally we'd say, well, for domain, all real numbers. For range, we'd say like, well, it can be anything, except remember, you have a minimum here again. So we can say, well, if we plug in 0, we get the cube root of 4. If we plug in 1, we get the cube root of 5. That's bigger and bigger, right? If we plug in like something small, 0.1, we get the cube root of, I don't know, 4.01, I guess. But I don't think it's ever going to get smaller than cube root of 4. So cube root of 4 is the minimum here. And then we go out to infinity. Domain, notice for this, is really easy. All reals, all reals, all reals, all reals. No issues. It's the range that you kind of have to rack your brain about on these. Right? What about these polynomials? This can get tricky. This is a factored out version of some sort of x cubed, right? If I were to FOIL this together, I would get 2x cubed plus some other stuff. There are no restrictions for polynomial graphs. And because it's 2x cubed plus some other stuff, we should know that that graph does something like that, right? So that means that its range is all reals as well. Well, what if I cube root that? Cube roots are allowed to be taken of positives, negatives, or 0, so it doesn't change my domain. And that still allows the range to be anything as well. You could have a tiny y value, you could have a 0 y value, you could have a huge y value. If we're fourth rooting, now we have to pay attention to, we're not going to do range for this, we are going to pay attention to domain. Okay, think about the 3 values that cause this thing to be 0. X equals -2, x equals 1, x equals 3. You have some options here. You can say, oh yeah, I remember these graphs do something like this. Where the graph is below the x-axis, that represents where the graph is negative. Where it's above the number line, that's the x-axis, that's positive. And we want the positive sections, right? We can only even root a positive. So we want anything between -2 and 1, and then anything from 3 to infinity. Now, again, I'm sort of challenging you on this because all of these polynomial inequalities, I haven't formally taught this to you yet. We've been doing just linear stuff. But I want to throw it out there because some of you might remember this. I'm not going to put these polynomial ones on our homework quiz, but I just want you to kind of start thinking about it. Domain and range can get pretty tricky. Okay, just a couple more. Number 7. Same thing. Let's take a look at this. What would this be if I FOILed it out? 5 times x times -x times x. You're going to get -5x cubed plus some other stuff. That's one of the cubics that look like this. It goes down on the right and up on the left. So what can I plug in? Anything. What can I get out? Anything. If that same polynomial is under an odd root, what can I plug in? Anything. What can I get out? Anything. If I put it under an even root, now I've got to think about where the thing is positive and where it's negative. I want the positives. There are 3 different values that will make this 0. We've got -1, +5, and +4. So in order, -1, 4, and 5. Instead of testing a number in each section, I'm going to copy this shape of the graph like that and say, here's a positive section and here's a positive section. Domain is -infinity to -1 and 4 to 5. All right. Again, I don't really want you panicking about the polynomial stuff or the quadratic stuff. Those are really challenging questions. When I quiz you and homework quiz you, we're focusing on the linear pieces. So more like questions 1 and 2, the ones on the front page. But this is sort of a preview of what's coming down the road too. Number 8, domain and range of 4x minus 5. That's linear. Easy peasy. What if we make it 4x squared minus 5? That is now quadratic. Something like this, right? You can still plug anything in. But now there's a minimum value and it goes up to infinity. So what's the minimum value? Well, this is just 4x squared minus 5. That means instead of starting at 0, 0, it starts down at -5 and goes up to infinity. What if we make it 4x cubed minus 5? That's a cubic, right? Now I'm not being very accurate with my graph here, but we can plug anything we want in for a cubic and we'll get anything out as well. What about number 11? 4x squared plus 5. Instead of shifting the parabola from 0, 0 down, it shifts up. I can plug anything in, and I'm going to get the vertex to infinity out. The vertex is at +5. All right, what about the square root of x plus 5? X plus 5 greater than or equal to 0. So -5 to infinity. A square root graph, y can equal 0, yes. A square root is always positive. Positive. Okay, so we've got 0 to infinity. What about this? -x squared minus 5. We need -x squared minus 5 to stay greater than or equal to 0. Is that even possible? We need -x squared to stay greater than or equal to 5, but if we divide by -1, that's saying we need x squared to be less than or equal to -5. However far you need to get to this to realize this is always negative. You can plug in a tiny number for x, but it's still going to be -x squared minus 5. Plug in a huge number for x, it's still going to be -5. We can't square root a negative, so this graph can't exist. If you try to graph this thing, let's just try to graph it. Square root of -x squared minus 5. It looks empty. Oh, zoom 6. It looks empty. And it's not stuck or thinking. It's just like, yeah, that looks like nothing. There are no real numbers on this graph. So it has no domain and range. It's not really a function. That can't exist. What about 5 minus x? That's got to stay greater than or equal to 0. We did this in class. I like to just show it like this. Instead of subtracting 5, dividing by -1, flipping the symbol, just move the x to the other side and recognize that if 5 is bigger than x, that means x is smaller than 5. -infinity to 5, including. This is still going to be 0 as a minimum range and infinity as a maximum. meaning this will just keep continuing to grow without bound. It just goes off to the left instead of to the right. What about the domain for number 15? We said negative x squared minus 5 is always negative, and it's never 0, right? If you graph just this piece, ignoring the 1 over part, you've got a graph that's been shifted down 5, and it opens down. So what can I plug in for x? I only care that negative x squared minus 5 doesn't equal 0, and it never does. So that means that I can plug in anything. Use my all real numbers. I can plug in anything for x, and I'll get 1 over something negative. And speaking of that, for the range, 1's on top, so y can't equal 0. I will always get 1 over something negative, which will always divide out to a negative. So negative infinity to 0, without including 0, is the range. These last three are rational graphs. All right, so let's look at these. X plus 5 can't equal 0, so x can't equal negative 5. Negative infinity to negative 5. Negative 5 to infinity. There's a 2 on top. That still means that y can't equal 0 because there's no x up there. And then you've got 2 divided by x plus 5 can come out positive if you plug in a big enough x number. And it can come out negative if you plug in a negative enough number. So we've got negative infinity to 0, 0 to infinity. All right, 1 over x minus 5. X can't equal 5, so that we don't divide by 0. Y can't equal 0, but you get 1 divided by x minus 5. Sometimes it's positive, sometimes it's negative, depending on what you're plugging in. So you can get both positives and negatives, just not 0, out of that range as well. What about 18? 5 minus x can't equal 0, so then x can't equal 5. But it's still the same scenario, same answer as before. We can get both positives and negatives out of those y values, we just can't get 0. All right, what about this section? We just keep going and going, right? Okay, let's see. 19. So we only care about the denominator. X can't equal 0. So our domain only is negative infinity to 0, 0 to infinity. This 1 minus x up here does not matter for domain. What about down here? 3x minus 18 can't equal 0. Add 18, divide by 3. X can't equal 6. 21. Again, we're only doing domain. X can't equal 5. We don't care about the x plus 3. If I asked you about domain, we'd have to talk about horizontal asymptotes, which is not quite yet. So if you remember those rules, you can figure out the range. But for now, we're just doing domain. Oh, what about x cubed minus 5? X cubed minus 5 means that x cubed can't equal 5. And even though 5 doesn't have it's not a perfect cube, you can still write that x can't equal the cube root of 5. And remember, odd roots do not have plus or minus. So this is just negative infinity to the cube root of 5 and the cube root of 5 to infinity. 3x plus 24 can't equal 0. Solve that, you get x equals negative 8. So everything excluding negative 8 is in our domain. What if it's 3x cubed plus 24? Then x cubed can't equal negative 8. Negative 8 is a perfect cube. It's just x can't equal negative 2. Remember, no plus or minus. Cube root of negative 8 is negative 2. So negative infinity to negative 2 and negative 2 to infinity. Back to quadratic. No issues with domain. What about the range? Well, the range needs the vertex. The vertex Because remember, I'm not going to do an x and y axis. This is a parabola that opens up. We want to know what is the y coordinate of the vertex. It's going to be something to infinity. So the vertex formula is negative b over 2a. That's negative 1. So we've got to figure out what's h of negative 1. If you plug negative 1 into this, you get 1 minus 2 plus 4. Negative 1 plus 4 is 3 to infinity. 26, this is the quadratic I like. S of t equals 2t squared minus 10. We can plug anything into that. The reason I like this is because if it doesn't have a middle term, you can just say, oh, it's been shifted down 10 units. So I know that the domain starts at negative 10 and goes up to infinity. 27, A and B are constants, meaning those are numbers. B is not equal to 0. The domain, we don't care about A and B. The domain is just x can't equal 0, so negative infinity to 0 and 0 to infinity. All right, now I have domain and range for this last one, and again, C and D are constants, numbers. C can't equal 0. So this is some sort of quadratic. We can plug anything in that we want. And then it kind of depends. C and D are constants. Are they positive? Are they negative? Are they a combo? Let's think about this. Let's start with they're both positive. C is positive, D is positive. What does that graph look like? The parabola opens up and it's been shifted up. So if C and D are greater than 0, the range is going to be D to infinity. What if C is negative and D is negative? That parabola has been shifted down and it opens down. So if C and D are less than 0, the graph goes from negative infinity up to D, right? And D is negative, so I'm not writing like negative D because it would just be like if this were like negative x squared minus 4, then I'd go up to negative 4. What if we get a combo though? What if C is greater than 0, D is less than 0? What does that look like? The parabola opens up, but it's been shifted down. The parabola opens up, but the whole graph has been shifted down. So if C is greater than 0 and D is less than 0, the graph starts at D and goes up to infinity. Last scenario, what if C is less than 0, D is greater than 0? The graph opens down, but it's been shifted up. If C is less than 0 and D is greater than 0, the graph goes from negative infinity up to D. Kind of tricky, right? Good to think about all these scenarios. Maybe you thought of one in your head. I'm assuming if they're both positive, maybe. But, it just says C and D are constants. It doesn't say that they have to be positive. Okay, I know that this is difficult. Your head might be kind of spinning after this packet. If you're thinking or you're worried about what's going to be on this homework quiz, we are focusing more on problems like the beginning and like we had in our notes. These first few, where I give you linear pieces and just shift the linear expression around under different things. Okay? All right, please come to office hours if you have questions. We will be practicing domain and range and talking about them all throughout the year. So this is not just like a 2-day thing and then we're done. It will take some work and some practice and some understanding.